Hello, we are going to continue with trigonometry. In this session, we are going to look at special angles. Special angles is about certain angles whose sines and cosines can be calculated quite easily. Usually we can find the sines and cosines using a calculator, but for some angles we can actually do it by calculating by hand. So let's look at some examples. The simplest case we start with is 0 degrees and 90 degrees. Now let's remind ourselves what sine and cosine means. We have a right-angled triangle. That's the right angle. That's an angle that we call theta. The sine of the angle theta is equal to the side opposite to the angle divided by the longer side, which is called the hypotenuse. So let me write that down. Sine theta is equal to y over r. The cosine of theta is the side adjacent to the angle divided by the hypotenuse. So that's x over r, and tangent of theta is the side opposite divided by the side adjacent. Y over x. Alright, now let's take a look at what happens when the angle theta is 0 degrees. If you look at this triangle, what does it look like if the angle theta is 0? The longer side would come right down until it meets the x-axis, alright? And the y will be 0. So if I were to if I'm to try and draw such a triangle, it would look like this. That's the x, that's the base of the triangle. Alright, but the r here would come right down so that the angle is 0. So r is just the same as the x. Alright, so my angle is 0 degrees, and the side opposite, the y, is just here. That's the y, which is also 0. The height is 0. Okay, so I know that y is 0. So that's what it looked like. A rather unusual triangle. It's really just a straight line. But this means that it is quite easy to calculate the sines and cosines. Let's try that. So sine of 0 degrees would be the side opposite, which is 0, divided by r. So it's 0 divided by r, but that is just equal to 0. So we have the simple answer, and you can check with your calculator that it is indeed 0. What about cosine 0 degrees? Let's try that. That's the angle. We have adjacent, which is the x, divided by the r. Now, but in this case, it is special because the adjacent, this side x, has the same length as r. They are equal. So the x is really the same as r. So we just have r over r. Number divided by same number. The answer should be 1. So cosine 0 degrees is 1. Okay, and we've got that quite easily. Finally, tangent theta is y over x. We know y is 0 and x is some value. So tangent 0 degrees is 0 divided by x. And we know that 0 divided by any number, as long as that number is not 0, is 0. So tangent 0 degrees is 0. So we have very easily found the sine of 0 degrees is 0, cosine of 0 degrees is 1, and tangent of 0 degrees is 0. Now you can try and remember that, but I would think it's easier if you remember this picture of the triangle. Just imagine a right-angled triangle, but with the angle come down to 0, so that the longest side actually meets with the base, and the height there is 0. Okay. And with this picture, you can quite easily read out the values of the sines and cosines and the tangent. So that's for the angle of 0 degrees. Now let's look at 90 degrees. When the angle is 90 degrees. So that's the triangle and that's the angle. Now imagine that we increase the angle to 90 degrees. Alright, from here, let's increase the angle. If we increase it to 90 degrees, now let me start by increasing it to just a large angle, maybe 80 degrees, and see what it looks like. So a very large angle will give a triangle that looks like that. Alright, that's the x, r, x and 1. Okay, imagine that we keep roughly the same r. Now you can see quite clearly that as the angle gets larger, the base, the side adjacent to the angle gets smaller. And you can also see that if this angle actually reaches 90 degrees, the y here, this opposite side, would actually meet with the r, simply because if that angle goes to 90, this angle must go to 0, right? Because the sum of those two angles must always be 90 degrees. So therefore, if theta goes to 90 degrees, this would turn into something that looks like a vertical line, r, alright, with the opposite side y meeting the r, and the angle, well, the base has come down to 0, x there equal to 0, and the angle is just the 90 degrees. Right? So once again the triangle has collapsed into a straight line. Longest side meets one of the other side. So we can now find the sines and cosines in a similar way. Right, let's do sine of 90 degrees. Okay, that would be opposite over hypotenuse, but this time the opposite and the hypotenuse are equally long. So our y over r is the same as r over r, which is the same as 1. So sine 90 degrees is 1. We've got our first answer. Then we do cosine 90 degrees. Right? Cosine is the adjacent to the angle divided by the hypotenuse, but this time the adjacent is 0. It has shrunk to 0, so it's just 0 divided by r, and that gives us 0. Therefore cosine 90 degrees is 0. Finally, tangent 90 degrees. Right, tangent is y over x, is the opposite over adjacent. Now this is tricky. Our opposite is y, but our adjacent has become 0. So we have a number divided by 0. Now you know that we cannot divide by 0. The answer is just undefined, meaning there is no number, there is no answer. So therefore, this is, we can say that it's undefined, but we can also think about it in another way. Imagine, alright, that you have, we know that tangent of the angle is y over x, is the opposite over the adjacent, and when the angle gets closer and closer to the 90 degrees, you can imagine that the adjacent, the x, gets smaller and smaller. So this means that y is divided by a number that gets smaller and smaller. Now in the end, that number goes to 0, but before it actually turns into 0, we can imagine that as y is divided by a number that gets smaller and smaller, the answer should get larger and larger. So we can say that when x, when the bottom of this fraction reaches 0, this answer approaches infinity. Right, so in mathematics, infinity means a number that is so large that you cannot write down a number for it. We just use this funny symbol. It looks like an H which is rotated 90 degrees, like a lying down, a sleeping 8, to represent infinity. Let me just write down the word. Right, infinity. I-N-F-I-N-I-T-Y. Extremely large, so large that there's no number for it. Alright, so that's theta equal to 90 degrees. So we have just looked at two special angles, 0 and 90 degrees, and we've seen how to find the answer just by looking at the picture. So, and again, of course, you can also find all these with a calculator if you really cannot remember what the answer is. But you might get questions which actually ask you to make use of these special angles directly. So they might either be given to you, or you might just have to try to work it out or memorize it. We are next going to look at a few other special angles. Now, the next two angles we'll look at is 30 degrees and 60 degrees. Okay. Now suppose that I start with $60. So that's 60 degrees. Right. And I want to find the sines and cosines. So say that's R, that's X, and that's Y, and that's X. So how can we find the answer without using a calculator? The trick is this. Now, notice that angle is 30 degrees. Okay, 60 plus 30 is 90. So that's 30 degrees. The way to do this is to draw an identical, exact same triangle on the other side, but just flipped around. Okay, so I have another right angled triangle here with a 60-degree angle as well. So that, now if you look at the whole shape, you see that that's 60 degrees, that is 60 degrees, that's also 30 degrees. So these two angles together make up a 60 degrees. All the angles are 60 degrees. So clearly this is an equilateral triangle. All three sides of the overall shape of the overall triangle are equal. Now, that's actually very helpful. Now, in order to make use of this to find the sines and cosines of these angles, the next step is to just think of a number to give to the side. It's like thinking of an example. Now we can do that because we have seen in the previous session that no matter what, no matter whether this right angle triangle is bigger or smaller, when you use it to find the sines and cosines, you will always get the same answer. Because whether you use a bigger or smaller triangle, they are similar triangles because they all have the same angles, and therefore when you take the ratios of the sides, you always get the same answer. So it really doesn't matter what number I give it. If I just think of some example number to give to the lengths of the sides, and if I can use that to find the sine and cosine of the angles, then the answer will be correct, even if I have a different triangle. So let's try that. Now, usually, to make things simple, we use the number 1 for the x. Alright? The x is just half of this side. So if this is x, that side is also the same, it's also 1. So that means the total length of the base is 2. And since this is an equilateral triangle, that side would also be 2 and that side would also be 2. Okay, so this is the number that I'm going to choose for the example. Now it's getting a bit complicated, this diagram. So I'm going to draw another picture. Okay, that's the equilateral triangle. And that's the right angle. That's our 60 degrees. Right. Now what this tells us is that this side is 2 and this side is 1. Okay, so this time I can actually leave out the other side now. So what I've done is that I've made use of this idea that I can make up an equilateral triangle like that to tell me that if the longest side is 2, then the shortest side at the bottom is 1. So I have 2 sides already for this triangle. Okay. Now I can then find the third side as well. How can I find the third side? We use something called the Pythagoras theorem. Let me write that down. What is the Pythagoras theorem? Right. If I have a right-angled triangle like that, and let's say the length of one side is A, the other side is B, and the longest side is C. If I have this right-angled triangle, then Pythagoras theorem, let me spell that, Pythagoras, tells us that C squared is equal to A squared plus B squared. Alright? So it's a formula for the sides of a right-angled triangle. And we can use this to find this other side. Now if I call that y, I can put these numbers into the formula. Let's see what we get. Now the longest side is that one, 2 is a C, so I have 2 squared is equal to, right, A squared, A is the y, right, A is the y, so that's y squared, plus the 1 squared. Now you see that we have an equation now. We can solve for the y squared. So 2 squared is 4, y squared is y squared, 1 squared is 1. So clearly y squared should be 3, so that 3 plus 1 is 4. Alright, y squared is 3, and therefore y must be square root of 3. We have all the sides now. We have all the sides of this right-angled triangle. And clearly, if we have all the sides, we can now find the sine, the cosine and the tangent. So let's do that. Let me just clean this off. You can easily read off the answers. Alright. Okay, I'll write it down here. Sine 60 degrees, cosine 60 degrees, tangent 60 degrees. The sine 60 degrees is, let me write down the y here. So y is the root 3. Y is equal to root 3. So sine 60 degrees is the opposite, is the root 3 divided by the hypotenuse of 2. Root 3 divided by 2. That's sine 60 degrees. Cosine of 60 degrees is the adjacent 1 divided by hypotenuse 2. So 1 over 2. That's a half. Tangent 60 degrees is the opposite of root 3 divided by the adjacent, which is 1. Root 3 over 1. So that's just square root of 3. So you've just found all the sine, cosine and tangent of 60 degrees. Now next we are going to do it for 30 degrees. And we can actually use the same triangle because this side is 30 degrees. So that's convenient. Now just to make life easier for us, I'm going to flip this around to the usual direction, like that. Alright, so that's the usual direction when we first learn about sines and cosines. And that's the 30 degrees. Okay, that's 2. Now the side opposite to 30 degrees is 1, so that's 1. And the side adjacent to the 30 degrees is root 3. So we have again a right-angled triangle where we know all 3 sides. So let's write down the answers. Sine 30 degrees, cosine 30 degrees, and tangent 30 degrees. Right, so sine 30 degrees is the opposite 1 divided by hypotenuse 2. Okay, cosine 30 degrees is the square root of 3 is the adjacent, which is square root of 3 divided by hypotenuse 2. Finally, tangent of 30 degrees is the opposite over hypotenuse, 1 over root 3. There we are. So we have all the answers now for the sine, cosine, and tangents of 30 degrees and 60 degrees. Now, these pictures are a little more difficult to remember, then the pictures are drawn for the angles of 0 degrees and 90 degrees. So in order to learn this, you can either choose to remember the pictures or to remember the actual numbers. Now I would much prefer to remember just the one triangle rather than to remember 1, 2, 3, 4, 5, 6 equations. That's quite a lot of equations to remember. Whereas if I simply remember one triangle, I can think of this triangle as half of an equilateral triangle where the longest side is 2. If I think of it this way, I would know straight away that the other side is 1. Okay? And the only other thing that you have to remember is that this other side is square root of 3. If you are in the middle of an exam, you would probably not want to work through Pythagoras' theorem to find this root 3. So just remember, take an equilateral triangle with the side 2, and then the other side would be just half of the 2, and then the remaining side, there is a square root there, square root of 3. 1, 2, square root of 3. And once you can remember this one triangle, you can not only use it for the sines and cosines of 60 degrees, you can also just flip it over and use it to find the sines and cosines of the 30 degrees. Now there is one more special angle that I want to look at before we finish, and that's 45 degrees. So let me draw the triangle for this. Right angled triangle, degrees. Again, this is an angle where we can find the sine and cosine by simple calculation, like we did just now. The way to do it is, again, to think of some simple values, some example values for the sides. But before that, let's look at this triangle again. Now if this angle is 45 degrees, that's 90 degrees, then this other angle must also be 45 degrees. So once we realize that two of the angles are equal, this means that these two sides are also equal. Therefore, we have an isosceles triangle. Alright, in which those two sides are equal. So that's the opposite and the adjacent. The opposite is equal to the adjacent. So that's convenient. Now the way to do this is to let each of this side be 1. So if that's 1, that must also be 1. So that will be our example. And then we can find the longest side using Pythagoras' theorem. If I call the side C, okay, and that's my A, and that's my B. Now Pythagoras theorem says that C squared is equal to A squared plus B squared. So putting in the values from here, we have C squared equals to 1 squared plus 1 squared, so C squared is equal to 2. Therefore C is equal to the square root of 2. Therefore, we now have all the sides of this triangle, and this also means that we can find the sine, cosine and tangent. So let's do that. I want to find the sine of 45 degrees, cosine of 45 degrees, and the tangents of 45 degrees. Sine 45 degrees, sine of that angle is equal to the opposite 1 divided by adjacent also 1. 1 over 1, which is 1. Cosine 45 degrees, 45 degrees is here. That would be at the adjacent side, 1 divided by the longest r. Sorry, I've made a mistake here, haven't I? Sine 45 degrees. That was wrong. Let me start over. Sine 45 degrees, sine of this angle is the opposite, which is 1, divided by the hypotenuse, which is square root of 2. 1 over square root of 2. That's the correct answer. Cosine 45 degrees is the adjacent, 1 divided by the longest side, root 2. 1 over square root of 2 again. Finally, tangent of 45 degrees is equal to the opposite, which is 1, divided by the adjacent, which is also 1. 1 over 1. So it's 1 over 1, which is 1. Notice that sine 45 degrees is exactly the same as cosine 45 degrees. So this is something special for the 45 degrees angle, because it gives us a right angle triangle that is also an isosceles triangle with the two sides equal. And for the same reason, the tangent 45 degrees is equal to 1. So that's also a rather special case. So we will stop here for this session. See you next time.